Hello everybody! The goal of this maintainers track is to look at one of the main interesting parts of Falco. Falco is a CNCF incubated project that aims to provide cloud-native runtime security. We look at the part of Falco that uses gRPC as an output interface that exposes the rule alerts matched thanks to an eBPF program able to trace all the syscalls happening in the kernel. Falco was created as an open source project from day one by Sysdig in 2016 to parse libsysp events to match security policies against them at runtime. About 2 years later, it was donated to the CNCF. This past January, Falco has been the first ever runtime security project to be promoted to the CNCF incubation level. Anyways, my name is Leonardo. I'm an open source software engineer at Sysdig, where my daily job is to code Falco, evolve it, and maintain it. As a maintainer of Falco, I also have to advocate and present its technology and all the hard work we do to continuously improve it. So here I am. Here there's a photo of me moving heads like a real Italian in San Diego. Falco swag to the first one guessing the exact meaning. You can usually find me on Twitter, GitHub, and generally the webverse with the nickname Leonardo. Feel free to drop me a line, follow me, ask me questions about Falco, eBPF, kernel, whatever. No problem at all. I like to socialize. The plans for the next 30 minutes are to look at photos of my beautiful homeland in southern Italy, while trying to get a skin on how Falco solves the runtime security problem, even for cloud-native environments based on our beloved Kubernetes, by tracing the syscalls using a cool kit technology called eBPF. Finally, we will see how Falco collects these events from the kernel as tools against them, and how it eventually outputs alerts via gRPC to make them more usable in a cloud-native context. Since we're gonna deep dive into all of this, by the end of this talk, you'll have a deep technical knowledge of some very crucial parts of Falco, and hopefully you will be also able to start contributing to it. What does security mean, at least to me? I want to control things that can happen and things that cannot. Since preemptive control is not always possible, I also want deep visibility into my systems to be able to know as soon as possible what just happened. I think of security in terms of two words, prevention and detection. What these two concepts have in common? Policies. Both use some kind of policies to describe the allowed or disallowed behavior for a process in terms of system calls, their arguments, and host resources assessed. The differences are that the first concept, prevention, is about enforcement. Do not allow some actions for some person to happen at all because of some policies. On the other side, the second angle of security is to use the policies to monitor the behavior of a process and notify when it steps outside those policies at runtime. Some examples of enforcement tools are eBPF, Linux, or Parma. Even the authorization mechanisms like Kubernetes Service or the policy-based admission plugins fit this category, since they will prevent something to happen depending on some policies. While tools like AuditD and Falco itself belong to the auditing side of the security topic, a topic that, especially in cloud-native security environments, has not been solved yet. Falco runs mostly user space, and this makes it somewhat a software target, but, on the other hand, this also makes it able to have a much richer set of information powering its policies. An augmented kind of policies, taking into account things like container metadata, that's very difficult to implement completely at kernel level. So, can Falco solve all our security concerns? Honestly, not at all. Software is made of layers, and so is security. This is even more true in cloud-native environments nowadays, as you can see in the scheme I drew into the slide. Falco is here to fit into this picture together with other tools. You'll have to combine it with other layers in many ways using a defense in-depth strategy. The idea is to defend a system against any particular attack using several independent methods. In case you are still not convinced that there's no such thing as perfectly safe software, and a layered approach is the best possible strategy for software security, just allow me to stress some points. How to trust cloud providers and their ability to detect malicious or compromised insiders. How to prevent an undisclosed vulnerability or a zero-day bug that allows someone to break into your systems. I mean, CVE still happens. Linux, Kubernetes, name an open source software that has not experienced the CVE and suffered an exploit. I think it's clear now that enforcement tools alone are not enough. We also need runtime security solutions, and these two approaches are and must be complementary and not mutually exclusive. So, what's runtime security? In the context I've just described, runtime security is often the last line of defense. Let's try with a metaphor. She's Kelly, look how beautiful she was. I have locks on my door and also an alarm, think of them as compliance rules. But she alerts me when things are not going right, policy violations, when little bro is misbehaving, think of him like a compromised insider, or if there's something suspicious happening outside or nearby, anomaly or 0 day. She detects runtime anomalies in my life at home, and she was, may she rest in peace, very serious about her job. I mean, look at her in the picture. So, while prevention is about locking the doors, detection is about continuously monitoring the inside and the perimeter. The Falco unique way to do this is by tracing and detecting everything happening inside the box from the bottom, the kernel, up, instead of using the usual top-down approach like other security monitoring engines do. How that's possible? Tracing syscalls at their source, and asserting rules against events containing the syscalls, plus other context info like arguments, Kubernetes metadata, container metadata, and so on. Somebody could argue, why tracing the syscalls? Well, nowadays the production environments are filled with so many pods, services, containers, monitoring tools, generally software. I tried to draw a nice layered diagram to slide before, and well, it turns out that complexity is the exact reason we go look under the hood. In the end, whatever program we run, it will end up making a lot of syscalls. This because system calls are the way programs ask the kernel, where everything happens, to perform some task. Whether the task regards networking, I/O, processes, this does not matter. Thus, instead of looking into every one of the hundreds of layers and abstractions we run our applications onto, the Falco approach to detect security threats at runtime is to go at the lowest possible level and trace all the footprints and the context in which they happened. We need to combine these events with metadata from other layers of interest like Kubernetes audit logs, container metadata, and so on. For example, we need to have the syscall arguments in a readable way. We need to know when events are happening. Asynchronously, we also need to know if a syscall was originated in a container, what was the ID of the container, and from what image the container was created. Also, we would like to know the cluster nodes where all of this happened. How to get syscall to user space and use them as one of the inputs for runtime security. Falco solves this with 3 alternative approaches that we can call Falco drivers. A kernel module, a ptrace-based producer we call pdig, which is slower than other methods and very hacky, but it's the only possible solution in some environments like managed Kubernetes clusters, Fargate, and places where you cannot install a kernel module, either eBPF probes. And finally, an eBPF probe. Forget the first 2 drivers I mentioned. In this talk, we are gonna focus only on the latter. Before or while using something, it's good practice trying to understand what it is, right? eBPF is an easy way to program the Linux kernel. Unlike kernel modules, eBPF programs are guaranteed to complete without crashing. If you ever wrote a kernel module, I know you can feel the greatness of such achievement. So the name of this technology stands for Extended Berkeley Packet Filter. It's the evolution of BPF, a technology born in 1992 to perform very efficient packet filtering, avoiding unnecessary user space allocations. So eBPF is very flexible and capable of tracing almost any aspect of all major Linux subsystems, ranging from CPU scheduler, memory manager, networking, system calls, and so on. With eBPF, one can attach custom sandboxed bytecode to virtually every function exported via kernel symbol table without the fear of breaking the kernel. eBPF emphasizes the importance of safety when crossing user space boundaries. The in-kernel verifier will refuse to load any BPF program if invalid point dereferences are detected or the maximum stack size limit is reached. Loops are not generally allowed, and only a small subset of specific eBPF helper functions is permitted to be called within generated by the code. Thus, eBPF programs are guaranteed to terminate at some point in time and never exhaust system resources. Furthermore, the performance overhead induced by eBPF is often negligible, making it a great fit for monitoring and tracing heavily loaded systems. For all these reasons, eBPF superpowers are perfect for our need to trace all the syscalls. I know, we are most ready to look at our eBPF driver implementation, no worries. Let's first give a glance at how eBPF architecture works in general. Let's pretend we have an eBPF source file ready. The first step is to compile it to eBPF bytecode. Once it is successfully compiled and the object file is generated, we are ready to inject it into the kernel, attaching it to a given hook or making it run on a specific event. For this purpose, we use the eBPF system call. This seemingly simple syscall does a lot more apart from loading eBPF bytecode. It attaches the bytecode to the event, and it also creates and manipulates in kernel maps. Then, the verifier statically analyzes the program before loading it, to ensure that it cannot harm the running system as we briefly explained before. And it's important to observe how there are plenty of events to which we can hook up various BPF program types. We have events for monitoring and tracing purposes, others for security, others for access control, and clearly for networking too. Finally, eBPF also provides the ability to access shared data structure such as eBPF maps. Well, the eBPF maps are likely the most compelling feature of eBPF. Without any doubt, without maps, and the Falco driver will not have been possible at all. Maps come to the rescue for sharing state between user and kernel space. They represent a very efficient in-kernel key value store for data aggregation and can be accessed asynchronously from user space. There are many types of eBPF maps, as you can see looking at the slide. Maps that store data per CPU, usual hash maps, arrays, maps to store other eBPF programs to tell call later that we use a lot in our driver, and so on. eBPF does not allow you by design to move memory from kernel space to user space, and for reasons. Its purpose to be safe would have been a completely false hope in that case, but luckily, as said, eBPF has maps. As you can see in the diagram here, the eBPF maps are a vital part of the Falco architecture when using the eBPF probe. Here we have a library called libscap that loads the half of the eBPF driver into the kernel eBPF virtual machine, which executes it. Under the hoods, libscap also sends little eBPF programs to be executed at runtime. The goal of these little eBPF programs that we call fillers is to augment the traced syscall so that in an input event we'll have the actual value syscall parameter head, not some random x values. At this point, eBPF does its magic and data flows to libscap and then to libsysp thanks to those fancy eBPF maps. Now, libsysp can finally enrich the events flowing in with container metadata and all the other fancy cloud native things we said. Suppose you want to contribute to our eBPF driver now. The first step will be to build the existing one from source, right? So, create a build directory, go into it, configure cmake to create makefiles to compile the eBPF probe 2, as shown in the slide. Once this configuration step is done, execute make-bpf to build it. If everything went well, you will end up having a .2 object file, the Falco eBPF probe, into the build/driver/bpf directory. Pretty simple. As long you already have Clang installed, the headers for your specific kernel release installed, and the debug file system mounted. Well, the next natural step is to load the eBPF probe we just built and use it as the Falco inputs driver. Long story short, you can execute Falco putting before its binary the Falco BPF probe environment variable. It can be either empty, in which case Falco expects the BPF object file to be into the .falco/falco-bpf.2 file into your home directory, or directly pointing to the path where you put the compiled BPF object file. Let's now dive into some details. So, what does happen when we run Falco with one of the two commands in the previous slide? First of all, the provided arguments are passed. Then, Falco instantiates the Sysdig class obtaining the inspector, which is what we call libsysp. It passes this inspector instance to the Falco engine, which in turn also parses the rule set we started Falco with, and to the Falco outputs, which is the piece of Falco responsible for initializing the output methods and handle the events when they will flow in from the inspector. At this point, Falco is ready to instruct the inspector to start live capturing syscalls, their arguments, the context within the happen container metadata, generate what we call input events. It does so by calling the open method of the synsp class, which starts the capture by calling the scap open method of the libscap library. The libscap main duty in this scenario is to actually load the eBPF program into the kernel and finally start the capture. This only slide will need a whole talk dedicated to it, but let me try briefly summarize it. To perform the loading, it first tries to locate the eBPF object file depending on the environment variable we passed to Falco before. Then it collects some machine info like the number of online cores, enables a eBPF just-in-time compilation for better performances, and starts parsing the half of the passed-in eBPF object file. While parsing it, libscap first checks if the eBPF probe version has been compiled for the current kernel release, and if the eBPF version matches the one that the current Falco version requires. Then it looks for eBPF map sections into the ELF to define and create them accordingly. The eBPF probe uses various maps to define and share its setting, its state, and its behavior. It has a map to represent syscall through system-independent codes. Look for syscall code routing table. A map to represent whether a specific syscall should be traced or ignored. Look for syscall table. Another map to describe the events in terms of the syscall they are created from, its argument, and their types. Look for event info table. A map to link every syscall to the entry and exit fillers to execute when it occurs. Fillers table. Then it has also maps to store measurements about all processes and threads per CPU. libscap loads all of these from the ELF and populates them. Then it looks for ELF sections starting with tracepoint or row tracepoint prefix and loads them too. To do so, it uses the BPF syscall using BPF prog type tracepoint or BPF prog type row tracepoint. Once loaded, it attaches them either by opening the tracepoint file in the debug file system and using ioctl command with perf event ioc set BPF flag, or by using BPF row tracepoint open BPF command for row tracepoints if they are supported. When a tracepoint with a BPF program attached to it fires, that program will be run. And this is how our BPF driver traces all the syscalls. Finally, libscap looks for ELF sections starting with the filler prefix. It grabs the corresponding BPF program from the fillers table and setups it to be executed when the related syscall gets traced by populating the corresponding eBPF map of type BPF map type prog array. These little eBPF programs are responsible for reading the syscall arguments at the entry or the exit of the corresponding syscall and make them useful for libsynsp. Alongside, libscap also retrieved the process and user lists, and now it is ready to scan the proc file system to gather thread IDs, read sockets, retrieve various other process information. Now, how all of these events are carried to user space? Well, Falco is now ready to go grab them. To do so, it simply loops through the events by continuously calling the next method of the inspector. Such method does three main things. It gets the pending container events, if any, it calls the scapNext function of libscap, and updates the Kubernetes state by connecting to the Kubernetes API server and asynchronously collecting its metadata and events, reconciling them later with the corresponding event. The piece of code responsible to effectively grab the syscall events is again into libscap. It's the scapNext method that reads the actual events collected into the BPF maps we mentioned before. Once this process is completed, we do have the input event at the user space level, and we instruct the Falco engine to check it against the currently loaded Falco rule set. If a match with a rule is found, the event gets immediately passed to the Falco outputs, which will handle it by calling the handle gRPC function in this case. This function reshapes the information contained in the event to create an output alert and push this final object to a queue, from which the actual gRPC implementation will pop. Let's now peek into the design of a gRPC server and one or more gRPC methods to serve those alerts. gRPC is an gRPC framework originally developed by Google, where it was called Sysdig. Then it was open sourced under the CNCF umbrella and evolved a lot since then. For sure, it's one of the more high-performance, standards-based, general-purpose and feature-rich gRPC frameworks out there. It's built on top of HTTP2, which is a binary protocol that implements the same semantics of HTTP protocol, making more efficient use of network resources. It also provides some nice capabilities like stream multiplexing within a single connection, flow control, and header compression. Usually, gRPC implementation use some generated code obtained from serialization formats that define the services you want to implement in terms of gRPC calls, their type, and their messages. Very often, but not always, this format is protobuf. Such generated code hooks into the core APIs directly, which is the API implementing the main features of the gRPC on top of a lower level API like system calls and transport protocols. Depending on the programming languages we use, gRPC has slightly different stacks. Since Falco is mainly written in C++, we are gonna look only at the gRPC stack, as depicted on the right part of this slide. At the bottom, we do have TCP as transport. Going up, we have CHTTP2, which is a custom HTTP2 based transport implementation that uses gRPC data structures and is heavily optimized for it. But you can also bring your own, such as ChromeNet, the Chrome networking library. Above, we have the gRPC core, where the main functionalities are implemented as said, and where a thin C API is. This thin C API is meant to support rapid languages implementations like the C++ one. To go synchronous or to go asynchronous, that's the question. The gRPC programming API comes in both synchronous and asynchronous flavors. These two closely correlate to the threading model in play. The asynchronous model gives the application code full control over the threading model. The synchronous model can surely handle multiple requests in parallel, but they are serviced from a gRPC thread pool. So, in the synchronous model, the implementer only has to care about handling the actual gRPC call and implementation, making it an easier model to work with. But, if you want finer control over the threading aspect of the gRPCs, then the asynchronous API is the better model, even though it's considerably more difficult to work with, honestly. In this model, the application tells the gRPC core that it wants to handle an gRPC and provide it a tag that acts as a key for the completion of events. Then, it blocks on a completion queue waiting for a completion key to become available. Once the key is available, the application code executes the associated gRPC. This model provides the best performance to who is willing to go the extra mile. The cost to pay is that such API needs considerably glue code to be written, and we will see in a bit, and a good amount of patience to deal with implicit behaviors that docs do not call out very well, honestly. But in the end, it allows us to bring our threading model and to overcome scaling limitations. Since no one knows when some Falco rules violation happens, I needed a way to let people start a gRPC and have it just sit there waiting for some violation to happen, so to notify the clients watching. I want people able to say, "Hey Falco, I am interested in violations about this topic." And Falco will tell them the violations regarding that topic, if any. And then, if other violations occur, it will go ahead and immediately send them to the people still watching. This way, clients would need to wait and start new gRPC calls randomly. While this mechanism serves well the just described use cases, it also reduces the latency. It reduces the per alert setup cost, and it gives us some sort of pipelining of Falco alerts. This is what is usually called long-lived streaming API. Long-lived RPC are calls lasting minutes, hours, or even days in some cases. As you can see in the slide, I use this gRPC bidirectional API to define and then implement it. Anyways, long-lived RPC do not come for free. There are a lot of complexity involved both in the implementation of such APIs and into their own nature. For example, the gRPC flow control may have large buffer. Retry strategies at the framework level stop having much sense in this case, which means we need to implement our own at the application level. Furthermore, we also know that this type of service fails when there are TCP disconnects, and also it takes time to detect such network failures. We also know it creates issues with load balancers. The alternative is that a Falco client does a RPC call and asks if violations already happened to the Falco gRPC server. In case they happen, the client receives all of them. Otherwise, it comes back to sleep and it will try again later, issuing a new RPC of the same type. Since having long-lived RPC as the only approach would not be sufficient to fit all use cases, I ended up providing also this approach by implementing a server streaming RPC. The client does a single request to the server, Falco, which can stream back as many alerts he needs to send, and then, if it does not have any other alerts left to send, it completes the RPC. It's like emptying a queue of Falco alerts at once. So, just to recap, the Falco gRPC server implements the bidirectional and the server streaming RPC for outputs. This way, we can eventually start more RPC calls without blocking its current thread. Honestly, as you can imagine, this process was not easy at all, and it's far to be yet completed, but after writing eBPF code, nothing can scare us, right? Improving the performances and the behavior of the Falco gRPC server was essential. So during the development, I needed to use various tools to profile it, like gproof and pproof, trying to maximize the time spent on syscall, since more syscalls time means better overall application performances. You can see a bit of this process in place in pull request 1241 if you are interested in learning more. I can say that in general, what matters when implementing such gRPC APIs in C++ is to use the asynchronous API, tune the threading model while also reducing the contention using tools like Valgrind or mutrace by making different hypotheses and measuring the outcomes. For example, I found that having a number of threads equal to the number of online CPUs works pretty well for Falco. You should also tune the number of completion queues. Having a completion queue per thread is known to be the best performance trade-off in common asynchronous use cases. Also, you should try to reduce the allocations and try to reduce copies. Anyways, as said, I consider the current Falco gRPC APIs far to be definitive. For sure there are still a lot of areas where performances can improve, but also, from an architectural point of view, there are still existential questions to be answered. For example, does it make any sense to design the outputs API as a unary call rather than a long-lived bidirectional streaming one? This alternative API would return a response containing the current list of Falco rule violations. Which use case not already covered up will it solve? Will it be more efficient? For sure it will be simpler to write and maintain. But how to decide? We need to weigh whether the added complexity for streaming long-lived RPCs provides a large enough benefit or not, and in which scenarios. Sending a message on a stream is indeed faster than a new unary RPC every time, but the improvement is fixed and has a higher complexity. So this is not a done deal yet. As said in the previous slide, the only real way to find answers is to write the code and measure it. So I invite anyone willing to take this task to join our community code and discuss this with us. Let's now jump into some diagrams to describe the current Falco gRPC flow in more detail. We are at the point that Falco can now read the configuration file and initialize the gRPC server by providing it config values like the serve paths and the address to bind. It also automatically guesses the number of online cores and uses this number as its threadiness value. At this point, Falco is ready to spawn a new thread responsible for running the entire gRPC server, which main operation is to set up its own threading model as said. Finally, the server also ensures to stay awake until it's running or to stop itself otherwise. When the gRPC server is told to start, the first thing it does is to register the asynchronous services automatically generated from the protobuf definitions and get told of the completion queues. Once this is done, we can ask the gRPC core to build and start the gRPC server. Soon after, the Falco gRPC server spawns one thread dedicated to serving and processing the requests for every online CPU. And while doing so, it also allocates 10 different contexts of 3 different types, bidirectional, streaming and unary, for each thread. Think of them as sessions. These contexts contain references to the actual service implementation to call, process func, and to the generated asynchronous service method to start serving the session, request func. They have 3 main functionalities. Start the session, that we do as we allocate them right now, process it when requests are coming, and eventually complete the associated RPC or keep it going. Contexts also keep track of the state of the request, whether it is in the initial state, in the writing one, or in the finished state. When a new gRPC event is available from the completion queue, every thread process function running in its thread as said decides, depending on the context state, whether to ask it to complete and end the RPC or to process the current event. We use the address of the context as the tag uniquely identifying the current gRPC event available from the completion queue. When it's time to process the event, the request context dispatches the current concrete implementation of the RPC call using the reference contained into the process func. In the shown case, it calls the sub method that is responsible to pop the last Falco alert, if any, from the Falco outputs queue we mentioned before and write it into the response stream. In case there are more Falco alerts to pop and to stream, it continues to write them into the response stream. This operation generates another gRPC event and causes the completion queue to trigger again and restart the whole process. In case there are no more Falco alerts left to send, this process notifies the gRPC core to be able to read requests again. Also, this operation triggers the completion queue mechanism again, and so this bidirectional streaming API keeps going. We have an official Go client that uses a timeout mechanism for retries to avoid spamming the Falco gRPC server at application level. For sure, there are smarter approaches to implement, and this is one of those improvements area I was mentioning before. We also have an official Python client and a Rust one for the gRPC Falco APIs. Both need some serious love. So, regardless you're interested in contributing and improving the C++ Falco gRPC server and methods, or to the clients, please join our community and help us. Also, in case you need direction or support, feel free to drop me a line over Twitter. Always glad to help. So, thanks everyone for staying here for so long. My direct messages are open. You can find me with Leonardo nickname on Twitter or GitHub. Feel free to follow me, get in touch for even more details in case you don't have had enough. Ciao!